Okay. Okay, we're ready. So today we have David Wallace from the University of Pittsburgh. Thank you very much, David, for accepting the invitation.
Pleasure.
Okay, we're ready. Who will be talking about quantum gravity at low energies. Whenever you're ready, David.
Thank you. And thank you for the invitation. It's always, when I give an interdisciplinary talk like this, there's always a danger that, at least for some members of the audience, they know more about this than I do. So I can only apologize to them and hope to make it up to them in the questions. Okay, in the sort of philosophy of physics literature and in various other bits of the general physics literature, there are a bunch of claims made about quantum gravity. First of all, quantum gravity tends to be defined something like this. And I think this definition is largely fine. You'll sometimes see it said that quantum gravity is any physical theory which combines general relativity and quantum theory. Or slightly more carefully, it's any physical theory that has general relativity, classical general relativity as a limiting case, and quantum theory, or sometimes one might specifically say the standard model of particle physics as a limiting case, or as a partial approximation. In other words, it's a theory that reduces to classical general relativity in some regime, reduces to quantum theory in some regime, but in general combines them. And here are some fairly standard things we'll see, at least in these corners of the literature, about quantum theories of gravity. Here's the most common thing you see claimed: we don't have a quantum theory of gravity. Quantum gravity is a research program, an aspiration, a holy grail of theoretical physics, not an extant theory. To be more specific, we don't have an acceptable theory of quantum gravity in the sense that we have an acceptable quantum theory of the other interactions in nature, of the strong force and the electroweak interactions. Mathematical physicists and some philosophers might worry that whether because of the quantum measurement problem or the renormalization pathologies of quantum field theory, then maybe there's something unacceptable about those theories. I don't agree, but in any case, the claim is normally, even insofar as those theories are acceptable, we don't have an acceptable quantum theory of gravity. But here's the second claim. It's going to be a very difficult exercise to get one because empirically we don't need one. The second claim that gets made is something like, there are only exotic situations in which we need quantum gravity to describe them. The pre-inflationary era of the universe, or if there's no inflation, depending on your cosmological preferences, the super early Planck curvature period of the universe, some of the long-term exotica of Hawking radiation, maybe the interior of black holes, very, very remote empirical regimes. With the exclusion of those, it's claimed all known empirical phenomena either get divided, either get described by GR or get described by the standard model. There's a division of labor where there are phenomena described by classical gravity, there are phenomena described by non-gravitational quantum mechanics, and only super esoteric exceptions live in the intersection where you need both. So I want to say this claim is false. I think this is recognized in some corners, so in some ways this is an advertising exercise, but in any case, I think both of these claims are inaccurate. Here are some better claims, I think. We do have an acceptable quantum theory of gravity in almost exactly the sense that we have an acceptable quantum theory of the other interactions. Which is to say, we have an acceptable quantum theory of gravity in the sense that we have a quantum field theory we can obtain by just applying modern quantum field theory methods to the general theory of relativity. Now, that theory, to be well defined mathematically, requires a high energy cutoff. It doesn't work above a certain scale. It doesn't work even close to a certain scale. Without that cutoff, it's not well defined. The cutoff presages new physics that we don't have. But that's also true for the standard model. Our general take on quantum field theories in particle physics for the last several decades has been an effective field theory paradigm where the theory is only supposed to be descriptive within a certain energy range. And we can think about quantum gravity as descriptive in that range in just the same way. And understood that way, we have an abundance of observational evidence that supports quantum gravity in this sense. I'm going to call the theory of this kind low energy quantum gravity. Low energy means low energy relative to the Planck scale. This is not an especially demanding constraint. The center of a supernova, for instance, is an example of a low energy environment. More or less anything that would normally be described as high energy physics counts as a low energy environment. And within that low energy environment, there is a ton of empirical evidence to support the theory. The claim that you hear that says we hardly ever find phenomena that require both gravity and quantum mechanics to describe is just wrong. And a little sort of reflection on astrophysics and cosmology makes fairly clear why it's wrong. So let me start demonstrating that. Here's a small audience participation exercise. Pick up an object. I've got a pen. Hold it in the air. It shouldn't be a heavy or valuable object. Let go of it. Okay, you observe it accelerates downwards. You didn't observe it hit the ground because I haven't got the right camera set up, but the thud you probably heard is it's sharply decelerating as it reaches solid matter on the floor of the room. If you've just repeated that yourself, congratulations. That was a quantum gravity experiment. Who says high energy physics is expensive? Specifically, it's an experiment that requires both gravitational physics and quantum mechanics to describe it. You can't understand its acceleration downwards without gravity. You can't understand why it stops when it hits other solid matter without quantum mechanics. We know we don't have a classical stable theory of matter. It's a non-relativistic theory. You need to look a bit further afield to find an experiment that tests relativistic quantum gravity. You need a more expensive piece of kit. Specifically, you need one of these. The GPS system on your phone notoriously requires general relativity to work. The satellite networks that maintain GPS require keeping track of general relativity time dilation effects. The microcircuitry inside your phone requires quantum gravity, quantum mechanics. A full explanation of why your phone tells you where you are requires both quantum mechanics and general relativity. And similarly, those experiments that were done in the 50s to test relativistic time dilation using atomic clocks by taking them around the world, modern experiments that test general relativity using atomic clocks by lifting them up slightly in the laboratory, those clocks, atomic, photonic, optical, require quantum mechanics to understand them. The thing they're testing is a relativistic phenomenon. It's both it's an experiment involving both relativity, general relativity, and quantum mechanics. Okay, maybe that's cheating. In slightly more careful statements of what quantum gravity is and isn't, you sometimes see the claim that quantum gravity is something involving self-gravitation and quantum mechanics. Maybe the problem with my examples is they involve a background gravitational field and quantum mechanics. Maybe the right way to think there is as a division of labor. General relativity tells us the metric, then we do quantum mechanics against the background of that metric. That won't do either, though. Here's an example of a system of a self-gravitating quantum gravitational system. The Earth. Again, the Earth is solid. Again, solid matter requires quantum mechanics to understand it. Solving for the structure of the Earth is a self-consistency problem where you take the equation of state of the matter in the Earth and you solve it under the self-gravitation of the Earth. Philosophers might quibble that geologists don't really use quantum mechanics. Maybe one wants to worry that we only have a phenomenological understanding of the physics of the Earth's material. Example where we actually have full control of the physics, think about the sun. The equation of state of the sun is sort of, standard dilute gas, dilute plasma theory. We understand the physics of it pretty well. The sun is, again, a self-gravitating problem, but again, the full stable description of the sun requires quantum mechanics. We need quantum theory to understand nuclear fusion in the core. We need quantum theory to understand how photons percolate out to the outside of the sun. If the sun was a bit smaller, we need quantum mechanics even for the equation of state of the sun. Stars substantially smaller than the sun have a core of degenerate matter. Degenerate matter isn't held out by pressure, it's held out by the Pauli exclusion principle. Working out how degenerate self-gravitating matter stays up is explicitly an exercise in doing quantum mechanics and gravity at the same time. In white dwarf stars, the corpses of stars like the sun, like Sirius B here, you have exactly the same phenomenon. The star as a whole is explicitly held up by the Pauli exclusion principle against gravity. Okay, those are a bunch of examples then of where we have a combination of quantum matter and Newtonian self-gravity. But we can find plenty of examples where we need quantum mechanics and relativistic gravity. There's the Crab Nebula, the wreckage of a supernova from a few hundred years ago. Supernovae are incredibly extreme phenomena. You need full general relativity to handle them. Approximations won't cut it, or weak field approximations won't cut it. Quantum mechanical phenomena also crucial in the forming of a neutron star. So of a supernova, we have to understand the bounce as degenerate neutron matter forms in the core of the star, as nuclear fusion stops being exothermic. So I've seen it said that the supernova is one of the very few places in the universe where it matters that neutrinos obey the Pauli exclusion principle. In the case of supernova is a full-on case of needing general relativity and plenty of quantum mechanics, relativistic quantum mechanics even. We also see this in early universe cosmology. There's a significant radiation factor to cosmology in the early universe. The equation of state of that radiation is the equation of state for black body radiation. Famously, you can't understand black body radiation classically. Famously, that's one of the things that led Planck to the beginning of quantum mechanics. Early universe cosmology is general relativity coupled to quantum mechanically understood matter. So I want to claim that actually applications of gravity plus quantum mechanical theories of matter are just absolutely all over astrophysics and cosmology. If I go slightly further, let's sorry, let me back off and just give a statement of the form of that, because we can say something systematically about what the theory of gravity is that we're using here. So what we're effectively doing in all of these processes is we're calculating an equation of state using quantum mechanics. We're working out an expected value for the stress energy tensor or non-relativistic limits of it in quantum mechanics in regimes where fluctuations in that are very small. We've got macroscopic amounts of matter. And then we're plugging that stress energy tensor into the Einstein field equation in place of a classical stress energy tensor. That gets called semi-classical gravity. You'll sometimes see in bits of the quantum gravity literature the claim that it's an entirely theoretical idea with no evidence behind it. I want to claim that huge pieces of astrophysics and cosmology comprise evidence for it. In fact, we could say slightly more than that. If we ask ourselves what's the empirical evidence we have for general relativity as a whole, then the general model, the sort of models of general relativity we might have evidence for kind of have the following abstract form. We have something like the manifold, the metric on the manifold, some matter, phi here is a placeholder, whatever the matter might be. I have some dynamical equations for phi. I have the Einstein field equation, and I have some expression, I've got here curly T, which assigns a thing which has the right form to be a stress energy tensor that's functionally dependent on the matter and on the metric itself. That's the general form of a model of general relativity. And here are sort of four classes of models of that kind. Vacuum general relativity happens when there's no matter at all. Phenomenological general relativity happens when the matter is just put in as a phenomenological description, like it's dust or a perfect fluid, or it's some kind of idealization that lets us treat planets as points. Classical general relativity is in some ways the sort of cleanest and most beautiful version of this, where we say, okay, the matter is field theories like the Klein-Gordon field or the electromagnetic field. The field has an action. The stress energy tensor is defined by the action, and the whole combined system of Einstein relativity plus the matter fields is a sort of self-consistent dynamical setup. And then there's semi-classical gravity, where the matter is a quantum field, and we couple the metric to the expected value of the stress energy tensor. So let's look at the actual places where we see this applied in physics. So vacuum general relativity has lots of applications. Specifically, vacuum general relativity describes gravity waves when we're away from their material sources. It describes black holes. The theoretical calculations and the computational calculations of gravity waves being emitted by colliding black holes in pitch dark is a tour de force of vacuum general relativity, and gloriously confirmed at LIGO. There's a whole bunch of applications of phenomenological general relativity. Solar system physics is mostly phenomenological. A lot of the time in astrophysics and cosmology, we're putting in a phenomenological rather than a microphysically derived matter field. I've been arguing that there's loads of applications of semi-classical general relativity. I claim that effectively the rest of astrophysics and cosmology falls into that category. Although there's also a blurry distinction, I think, between what counts as phenomenological and what counts as semi-classical in this context. We're always cutting corners when we try to work out equations of state, and at what point you've cut so many corners that you've just sort of phenomenologically posited the equation of state with some vague clues from the quantum mechanics rather than derived it. That's a little bit of a movable feast. In any case, insofar as something's not phenomenological, our application in astrophysics and cosmology seems to be pretty much always semi-classical. Now, if you ask, what are the applications of purely classical general relativity? So far as I can see, there basically aren't any. Evidence for general relativity is evidence for vacuum general relativity or phenomenological general relativity or semi-classical general relativity. Okay, but there are limitations of semi-classical general relativity. I don't want to suggest that that's our quantum theory of gravity. All the applications I'm listing are places in which quantum fluctuations and the stress energy are really small. And that's unsurprising. We find that in semi-classical methods in general. If you use the Hartree-Fock approach, it's based on the idea that we can treat the electron cloud as sort of averaged out so that the pairwise electron interactions can be neglected relative to the sort of interaction with the electron mean field. It obviously fails in places where we have large fluctuations. If I take a big chunk of charge and I prepare it in a superposition of here and here, then of course we don't expect the test charge to move towards the average point of the two charges. We expect entanglement, we expect the superposition of test charge here, test charge moves this way, plus charge there, test charge moves that way. So what about situations in which gravitational fluctuations are large, i.e. where we've got superpositions of different stress energy distributions? Well, there's a famous experiment to look at this, which has exactly the same form as that electromagnetic superposition case I just gave. Page and Gaoka 40 years ago did an experiment where they literally measured a spin half particle or something similar. I forget the details. If they got spin up, they put a weight here, and if they got spin down, they put the weight over here instead. And then they measured its gravitational field to see whether you got that 50% of the time, that 50% of the time, or that 100% of the time. You will not be surprised to hear that what's on the screen at the moment is not what Page and Gaoka got. They actually got this result. I actually asked on Page a few years ago whether he actually had any expectation that there'd be any result other than that, and whether he was doing the experiment entirely seriously. And he said, thinking about solar system physics and about how the solar system was chaotic, and the fact that we seem to we don't thereby seem to find gravitational attractions not towards the actually observed matter, gave him quite a lot of confidence this was the result, but nonetheless it was good to test it. However, admittedly, there's something a bit foundational about the Page-Gaoka experiment. People are a bit suspicious of it. It's kind of smacks of the Everett interpretation of quantum mechanics. At the very least, it seems to allow us to talk about macroscopic superpositions. I want to claim actually that that really a rather wide swathe of quantum theories, not just the Everett approach, make the prediction that if you have semi-classical gravity, you'd see what we didn't see in Page-Gaoka. But it could be debated. It would still be nice to see if there's a less foundational, less sus situation where we can see that we don't just use semi-classical gravity, where the fluctuations of gravity matter. And there's actually a really important one. Our current understanding of structure formation in the early universe has that structure formation happening because of gravitational instability that magnifies up small perturbations. And our dominant, though scarcely unchallengeable theory as to where those fluctuations come from is their quantum fluctuations of the early universe, with the most popular way of doing that being something like fluctuations in the inflaton field. This is pretty clearly a case where if you try to use semi-classical gravity, you get the answer wrong. If we want gravitational instability, requires the gravitational field to be generated by the actual, or in many Wells terms, branch relative distribution of matter, not the expected distribution of matter. If I've got a quantum field fluctuating, then the expected distribution of matter remains entirely homogeneous and isotropic. And so under semi-classical gravity, the gravitational field would likewise stay homogeneous and isotropic. And indeed, if you look at the physics that's actually used in, say, for instance, Stephen Weinberg's textbook on this to model these quantum fluctuations, it's not semi-classical gravity. It's a sort of quantum gravity theory that you get in a slightly ad hoc way by quantizing fluctuations. Specifically, you split the metric into a fixed part and a fluctuating part, G equals G naught plus H. You treat the fluctuation as a field defined on the background G naught, and you put a hat on it. And that gives you a quantum theory of fluctuations. And then that's the theory you use to calculate the inflaton or whatever fluctuations and compare to experiment. And insofar as these theories of quantum fluctuations make specific, or at least somewhat specific predictions about the spectrum of moments of the CMB, and insofar as those predictions remain in conformity with experiment, then we can see that this is a regime that is at least not out of the reach of experimental testing. But this quantized metric fluctuations theory is also not super satisfactory. What's wrong with it? Well, how do we make this split? What justifies a particular split into fixed part and fluctuating part? Doesn't that split sort of feel in tension with one of what we think is the sort of deep philosophical lessons of general relativity, that it's a background independent theory, where we don't have like a fixed non-dynamical background against which physics plays out? And from the point of view of the rest of my talk, where did the semi-classical gravity theory go? What's the connection between quantum gravity in this fluctuation form and the semi-classical gravity that I've been arguing is ubiquitously being used across astrophysics and cosmology? Okay, so I want to present, for this talk, and for reasons of time, I'm going to do this only in sketch form. I want to present the fact that modern quantum field theory gives us a perfectly unified way of describing theories of this kind. And specifically, the form I have in mind is formulating our theory through a path integral. We're used to the idea that we can give path integral formulations of our quantum field theories. They give mathematicians conniptions, but they're extremely effective and practically useful. They define transition amplitudes in a field theory between initial field configuration and final field configuration as the sum over all the histories of the fields that interpolate between the configurations, weighted by a phase factor proportional to the action of each configuration. And we can do that perfectly happily in general relativity. We can perfectly well say, we'll have matter fields and the metric, and we'll just define the theory by that path integral. I don't want to claim that that is under full mathematical control. There are, heavens knows, the path integral in non-gravitational quantum field theory is not under full mathematical control. And there are certainly puzzles and pathologies in general relativity understood this way that are not present in the background case where we've just got physics on Minkowski space-time. But it's under tolerable control. In particular, it's under enough control that we can start writing down various calculations and approximations. Specifically, in non-gravitational quantum field theory, we have a thing called the background field method, which I'm not going to go through this slide. I'm happy to get back to this in the questions. Which basically lets us, just through a change of variables in the path integral, reorganize the path integral into a sum of fluctuations and a background, where there's a self-consistency requirement linking, requiring the background to be appropriately coupled to the fluctuations. We can do the same trick in quantum gravity, in low energy quantum gravity. We can, through a change of variables, evaluate the path integral as a sum of background field and fluctuations. If we do that, we get a dynamical equation out for the background as a function of the fluctuations. In other words, we have a self-consistency problem, very familiar from mean field methods elsewhere. We don't have just a positive background. We have a setup where we can find regimes where the theory can be analyzed as fluctuations around a mean value. The mean value is determined by a semi-classical equation set by the fluctuations, and the fluctuations include matter particles like neutrons and protons, as well as gravitons, fluctuations of gravitation. Again, I'm happy to talk about that in rather more detail. I've just given it as a quick starting point. The point to take away is that if you use modern quantum field theory methods, you have a background independent presentation of the theory as a whole through the path integral, and then you can find regimes, solution spaces of that theory, which can then usefully describe in terms of an expansion around the background, where the background obeys the semi-classical equation. So we can get out semi-classical gravity and our quantized fluctuation theories, not as sort of things we posited to begin with, but as things we calculate from as approximations to the underlying path integral defined quantum field theory. And again, using technology that we're fairly familiar with from thinking about things like spontaneous symmetry breaking in non-gravitational quantum field theory. Okay, so once we see we've got a quantum field theory of this kind, we can ask sort of more generally and broadly, what's the evidence for that field theory? And now, evidence for any quantum field theory, which is a super complicated object, involves evidence for it in various different regimes. So for instance, in quantum electrodynamics, we can ask, okay, what's the evidence for the theory in regimes where you can do semi-classical methods? What's the evidence for regimes in which quantization matters, but where interference between quantized modes doesn't matter? We can ask about when you can test it in regimes which you can treat as coherent perturbations of various kinds. And we can look at regimes where you've got macroscopic superpositions of charge distribution. If you sort of break down evidence for low energy quantum gravity in various regimes, I think it looks something like this. In the semi-classical regime, we've got strong support for low energy quantum gravity in both non-relativistic and relativistic aspects of the theory, as I laid out earlier in the talk. In the perturbative incoherent regime, the regime where I need to think about fluctuations but not interference between fluctuations, then I think we've got pretty strong support for it non-relativistically through Page-Gailka, through thinking about chaos in the early solar system. We have less solid support relativistically, but we have some through our analysis of the cosmic microwave radiation. You start looking at the perturbative coherent regime, where I can't treat the theory semi-classically. I need to think about superpositions of different gravitational, gravitating bodies or gravitational degrees of freedom. Then things get thinner. In the non-relativistic regime, evidence here would be something like, can we create superpositions of massive bodies which are self-gravitating and get out some physical result from that? This is somewhere at the moment there's not a lot of empirical support, but that's likely to change in the next few years even. I'm not an expert on the experimental regime here, but there are a variety of programs going on that are looking fairly exciting in working these things out. And there's also the sort of longer standing program that tends to be associated with Roger Penrose of looking to see if just superpositions of mass spontaneously collapse or kind of distinguish whether they suppress coherence. One place where I don't expect us to be testing low energy quantum gravity anytime soon is what you might call the perturbative coherent relativistic regime, the analog of when we do interference experiments with photons. To test the theory in a relativistic regime, I think you need to be doing something like a two-slit experiment with gravitons. In theory, low energy quantum gravity says you'll see the same phenomenology with gravitons as you see with photons, i.e. interference, but also discretization. The likelihood of us doing that experiment in the remotely foreseeable future is negligible, given it takes all of LIGO to detect a gravity burst from something the scale of a black hole, let alone detect one graviton at a time. And in the what you might call the macroscopic regime, where I'm looking at superpositions of mass here and different mass here, non-relativistically, you don't really need to go outside perturbation to handle that. You can handle, say, superpositions of mass in the solar system perfectly well as perturbations. We have theoretical tools to explore how this would go in, for instance, cosmology and black hole formation, or black hole evaporation, I should say, using the technology of stochastic gravity. But it's probably fair to say that while lots of interesting things have come out of that program yet, we haven't had a decisive empirical confirmation, some prediction in early universe cosmology that really relies on that. So takeaway is that I think there are regimes in which the evidence for low energy quantum gravity is really good. There are regimes where it's moderate. There are regimes which might change soon, and there are regimes where we're not going to test it anytime soon. So it's not on as strong empirical ground as quantum electrodynamics. That's not kid ourselves, but it's being richly spoken to by evidence. Okay, for the last part of the talk, I'm just going to say something about its limitations. And you can sort of split these into two. There are limitations of that background field method I was discussing. the background field method does rather rely on the fact that there are no really large fluctuations in the gravitational field. If I tried to have a superposition of black holes in different places, or I had very large fluctuations in the early universe, then the background field methods might be problematic. Arguably, the statistical mechanics of evaporating black holes is a place where semi-classical methods lead us astray, or that's a whole other talk. And then there are places where not only the background field method of solving low energy quantum gravity, but low energy quantum gravity itself fails on us. And the obvious case is genuinely ultraviolet physics. The black hole interior, pre-inflationary physics, in general physics where curvatures are close to the Planck scale. Now that, remember, is exactly the regime in which people have sometimes said that's where you'd have to go to test quantum gravity. And I think a sort of meta lesson of the talk is that a lot of the way people talk about quantum gravity in various corners of the literature conflates low energy quantum gravity in the way I'm thinking it out with what you might call ultraviolet complete quantum gravity. But the reason for a quantum gravity theory at the Planck scale would be that we want to do quantum gravity at the Planck scale. It wouldn't simply be that we have to go to the Planck scale to do anything we call quantum gravity at all. And of course, the most famous limitation of low energy quantum gravity is the cosmological constant problem. And I think one virtue of the framework I'm doing here is it kind of lays out how relatively straightforwardly calculational the cosmological constant problem is. So the general form of the cosmological constant problem is something like this. Associated with the quantum vacuum are some very large energy densities. The biggest of them are associated with 0-point fluctuations in the quantum field, and they show up when you do loop order calculations of the energy density. But there are also really large contributions to the energy density that come from spontaneous symmetry breaking. There's a condensate associated with the Higgs field with the spontaneous breaking of local gauge symmetry, local electroweak symmetry at around 10 to the 2 gigaelectron volts. There's another condensate associated with the spontaneous breaking of approximal chiral symmetry down in the, I guess, about 100 megaelectron volts range. These are nothing like as large contributions of 0-point fluctuations, but they're still large. Specifically, they're very large compared to the observed value of the cosmological constant. They're many, many orders of magnitude above what's actually observed. That's not a contradiction in theory, because the term in the Einstein equation proportional to G is a sum of a term that's given by the energy density of the quantum vacuum plus an actual parameter, the bare cosmological constant, if you like. But saving empirical adequacy requires us to tune the bare cosmological constant to a very precise and very large value. Whether that kind of fine-tuning is a problem or not is a whole other talk, but it's widely seen to be, at least in the high energy physics community. Now, if you look at least in the sort of philosophical literature on the cosmological constant problem, you find a narrative about this that sort of problematizes whether we should really think it's a problem at all. The narrative goes something like, to establish the cosmological constant problem, you need to firstly establish the vacuum energy is real. And people tend to do that by sort of talking about the Casimir effect and results of that kind. Then you need to see, can we trust the calculations of vacuum energy you do in quantum field theory? You can worry that they're divergent, and so this isn't a place where the theory is trustworthy. Then you need to establish that vacuum energy couples to gravity, something it's said that we have no direct evidence for. And because all of these steps are questionable, and they all require speculation about new physics, there's been this quite common line, at least in philosophy, that the cosmological constant problem is either a non-problem, or at least it's a heuristic for a problem that might arise in physics we don't yet have. Well, if we accept low energy quantum gravity, however, if you do a calculation and you calculate the semi-classical field equations to one loop order, there are very large contributions proportional to G. And in order to get approximately flat spacetime as a solution to the semi-classical equation at one loop order, you need to calculate the lambda term. You need to give a very large, precisely tuned value to the lambda term in that calculation. And this gets worse as you go to higher order. In fact, I've said one loop order, but I'm not even sure you wouldn't get some of it a tree order given the condensates. And the thing is, this just happens calculation. It just comes straight out of low energy quantum gravity. There's no additional speculative argument required. So if one buys the fact that, and come to that, it comes straight out of the semi-classical equation. So if you buy the claim that low energy quantum gravity is the general framework we're using to do quantum mechanical gravity context of the kind we're actually doing quite a lot in astrophysics and cosmology, then you're just running straight into the problem. If you actually want to try to do a calculation of, say, the quark gluon plasma inside some collapsing star, then you're using quantum field theory, and what your quantum field theory will predict is a very, very large energy density that you don't observe, unless you cancel it out very precisely with your choice of the cosmological constant. The way I think we should think about this is that this doesn't invalidate low energy quantum gravity, but it's an anomaly in low energy quantum gravity in roughly the sense that Thomas Kuhn advanced. It's a place where there's something puzzling about the theory. We don't like it. We kind of get on with it, but it kind of sits there as something we either expect to be able to resolve at some point, or as a hint that someday might be resolved by whatever paradigm comes after low energy quantum gravity. Okay, let me wrap up. If we treat general relativity as a quantum field theory, it's a fairly well-behaved effective field theory. Again, I don't want to exaggerate that. It's some, it has puzzles and mysteries even by the standards of quantized gauge theories, but it's under at least moderate theoretical control, and it's under sufficiently good theoretical control that we can construct and explore specific solution regimes in the way we tend to do in QFT generally. Semi-classical gravity and the theory of quantum metric fluctuations about a fixed background are, again, fairly well-behaved special cases of low energy quantum gravity. Again, I don't want to exaggerate. Again, there are puzzles and pathologies, but again, they're sufficiently solid to do calculation and refer those calculations to experiment and observation. There's lots of evidence for the semi-classical regime of low energy quantum gravity. There's at least some evidence for the fluctuation regime, and that situation is developing. And the cosmological constant problem can be understood inside low energy quantum gravity as an anomaly. As always with an anomaly, we could avoid the cosmological constant problem by rejecting the theory from which it comes. If we get rid of low energy quantum gravity, then the case for the cosmological constant being a problem gets a lot weaker, but there's a high cost. I mean, it's a general feature that anytime you've got an anomaly in your favorite physical theory, you can avoid the problem by getting rid of your favorite physical theory. Quantum mechanics has the measurement problem as a puzzle within it. Abolish quantum mechanics and voila, you've solved the measurement problem. Except that normally to solve the measurement problem, we want to say it's not enough to replace quantum theory with another theory that doesn't have a measurement problem. You have to replace quantum theory with another theory that doesn't have a measurement problem and reproduces the predictions of quantum mechanics. So likewise, while you get a cosmological constant problem unproblematically only in something like low energy quantum gravity, then simply getting rid of low energy quantum gravity is only the beginning of the story. If you do that, then it's still wide open what your alternative move would be. Okay, I'll stop there, I think. Thanks very much.
Thank you very much, David, for the very nice talk. I will pass on the host to Pierre, because I will unfortunately have to go in a bit. We have the Ehrenfest Awards ceremony here. Sure. But before, maybe I could just ask you something to start. So many of the how to say, the claims you make, as you know, will probably be very controversial in a large part of the community. I think the most common claim is that we have zero empirical evidence of quantum gravity. Although I tend to sympathize with the way you phrase things, I wanted to ask specifically about the fluctuations in the cosmological, in the CMB.
Yeah.
Do you have any, how to say, feeling of how accepted is it in that community that we already have evidence for quantum gravity, because people are, waiting to detect the B modes, the tensor?
Yeah. Okay, good. So again, it's a regime issue. So the and again, I should say, philosophers of physics are masters of no specific area here. I jump between areas, so I'll defer to experts on this. But my understanding is, if you look at the sort of basic level predictions of the CMB structure, like you see in say Weinberg's monograph on cosmology from maybe 10, 15 years back. It's quantum gravity in the sense that I'm quantizing a self-gravitating theory. I have creation annihilation operators for gravitational, which create or annihilate gravitational fluctuations. But in that theory, Weinberg's assuming that the graviton modes are frozen out. The gravitational distribution is entirely set by the matter distribution. So that's a test, if you like, in my terminology. That's a test of, well, it's a place where my terminology actually has a bit of a gap. It's a test of quantum gravity in the perturbative non-coherent regime, and in what you might call a sort of semi-relativistic regime. We need sort of relativistic treatment of the matter, but the relativistic degrees of freedom of gravity go away. So we don't have gravitons in that situation. If you want a richer inflationary model where you allow for gravitons as well, then again, as I understand it, you get these further mode predictions, which we haven't observed, but which are in the process of being looked for. Bicep claimed to find them and it fell apart. We're still kind of hoping there. So I guess, again, that's it's an example of my point that a lot sort of depends on exactly what you mean by quantum gravity, and different bits of evidence are going to tell on different aspects of the theory. I mean, the terminological advice I'm running with really here is to go with the idea that says, look, quantum gravity is what people said it was. It's any theory that combines gravity and quantum mechanics, and then recognize that there are lots of different regimes of theories of that kind, with the Planckian regime being the most extreme, and then ask what evidence we have for quantum gravity within those kind of regimes. So if somebody wants to say, look, by definition, by quantum gravity, I need gravitons, I need gravitational degrees of freedom, that's a legit way of using the word quantum gravity. But it's useful to clarify that that's what we have in mind. And it's also useful to clarify we have this theory, this sort of pieces of theory that handle self-gravitating matter absent gravitons, which is, which has a reasonable amount of evidence for it. They're not evidence at the strength of the evidence for QED or something.
Thank you. I leave it to that to give the chance to other people to talk.
Yeah, thank you, David. Hello, and hello, everyone. So I will take care of managing the questions. So if you have questions, please raise your hand, and then I will give you the possibility to speak. So Jonathan Oppenheim.
Yeah, thanks for the talk, David. I'm I guess a bit confused about what you mean by a test of quantum gravity, because it sounds like it's a very broad definition of what that would be. Like it almost seems like you're saying, well, I take this mug, it's made out of atoms, and so any way of describing it is quantum. And I guess what I feel you need is like a comparison, like this, like quantum gravity would predict this, and something else that's not quantum gravity would predict something else. And I guess I didn't hear that, and I was wondering if you had such a notion where you could compare what a quantum gravity prediction would be and what something else would predict.
Sure. Well, I mean, of course, the pen to some extent is rhetorical, but for the sake of argument, sure. Quantum mechanics about gravity predicts if I let go of the pen, it'll stay where it is. And I mean, we could debate about free fall frames and how you want to think about not gravity, but at least at some level, that's your starting point. And gravity about quantum mechanics predicts the pen will fall through the floor. I mean, I'm not super serious about that example. I mean, but what I'd say there is just, if you like, the regime of background gravity plus quantum mechanics is incredibly solid. We have a ton of evidence for that regime. It's probably not what many people mean by quantum gravity, but strictly speaking, it's a phenomenon where we require both quantum mechanics and gravity to describe it. I mean, I suppose a broader point I want to say is I think what it means to test quantum gravity is incredibly vague. It's kind of like if you say, what would it be to test quantum electrodynamics? Now with QED, we have such extraordinary precision measurements that you might think that the magnetic moment of the electron by itself is just the end of the story about evidence for quantum electrodynamics. But if you if you ignore precision, you just look at regimes, then you might want to say, look, there are different bits of evidence for different bits of quantum electrodynamics. There's evidence for black body radiation, there's evidence for the two-slit experiment, there's evidence for Hartree-Fock models of atoms. There's lots and lots and lots of different regimes of electrodynamics where we've got particular models and we make calculations, and they're all very strongly evidenced. I want to say, look, there's lots and lots of regimes of low energy quantum gravity. Some of them are very strongly evidenced, some of them are moderately evidenced, some of them are not evidenced at all.
If at a minimum I want that my theory should guide me, or let's say any experimental evidence should guide me in my theory, then it doesn't seem that like that feels like a minimum requirement. Like, for example, with we had the ultraviolet catastrophe or something where we told us we had to quantize electrodynamics, but I don't see anything here which would guide us in our construction of a quantum theory of gravity. Is there anything that you could point to which would say, okay, your quantum theory of gravity has to be like this? That seems to me to be what we mean by evidence.
Okay, I think I'd say, I think we have a theory of that kind. I think we have a quantum field theoretic description of gravity with, as a number normalized field theory with a cutoff around the Planck-scale. And that theory is a space that we can use to construct experimental tests, and problems and failures for that theory might point us to new physics at sub-Planckian scales. But at the moment, that theory seems to be what's tacitly in the background of a lot of our applications. If we look at how we do astrophysics and cosmology, we're basically doing semi-classical gravity. If we look at how we do fluctuation phenomena in the early universe, or how we think about sort of things like the Page-Galadka experiment, we're doing fluctuation, quantum gravity, linearized perturbation theory. If you ask how do we think about those in a unified way, well, we're not forced to think about them as unified features of quantum field theory, but it's at least pretty suggestive that that's how it worked in other bits of quantum field theory. So it becomes at least natural to take that as one starting point and then look to falsify it or explore it in its other regimes.
Thanks.
Thank you. Next question is by Marko Vojinovic.
Okay, can you hear me?
I can hear you. I can't see you.
Okay. Yeah, I'm sorry, my camera is off. I cannot turn it on. Okay, if I understand you correctly, the whole lecture, basically your thesis is that a low energy quantum gravity as at least to 1 or 2 loop orders in gravitons or something like that would be a sort of a viable low energy theory, like an effective field theory approach, right? And that's basically the message.
Yeah, and I don't want to suggest that's an original idea for me, just to be clear.
Yeah, okay, of course. But my question is the following: are you not concerned, in a sense, about the non-perturbative effects? I mean, a perturbative theory is not a complete theory. So where I'm coming from is basically that quantum gravity should be, the UV completion of the whole theory. So you really need to have a non-perturbative definition of the theory to have it really to nail it down, so to speak, in a completely theoretically satisfactory way. But so if you look at the perturbative regime of that theory, you might be missing something, some effects which are not visible in the perturbative regime or something like that. Cosmological constant can be precisely one of those aspects that is intrinsically a non-perturbative effect, which comes from the UV sector, but has its sort of effect in an infrared regime, which is not perturbative. You don't see it, and so on. So do you think that low energy quantum gravity is actually satisfactory from that point of view, or is it still something that is just a stepping stone towards a more serious theory?
Okay, so I want to distinguish between a theory being perturbative and a theory not being UV complete. So low energy quantum gravity, as I presented it, is absolutely not UV complete. It's an effective field theory. It cuts off at the Planck-scale. I want to claim the theory as presented is non-perturbative. I presented it just as a path integral. Now, to get predictions out of the theory, we end up wanting to use various perturbative regimes. That's true across the face of physics. The vast majority of what we do in quantum field theory involves perturbing around a certain semi-classical solution. And it's, of course, absolutely true that there may be interesting non-perturbative things to be found, and we should absolutely look for them. I think one of the virtues of having the effective field theory framework is it gives you a starting point of getting at that kind of thing. And to some extent, I think you can see stochastic gravity as exploring a sector which, I don't know if you want to call it perturbative or not, but is not the sort of standard scattering perturbation. I mean, what people mean by perturbative can sometimes be a bit vague here. I mean, I don't think there's any prospect at all of getting substantive, quantitative, exact results out of quantum gravity. I mean, we can't get substantive, quantitative, exact results out of the anharmonic oscillator, let alone quantum field theories.
If I may interject, my definition of what is perturbative and what is not perturbative is in a more rigorous sense what is an analytic and what is not analytic. So the effect that can be expanded into power series, basically, that is perturbative, and there are effects which are not expandable into power series. So that's what I mean by it.
Okay, good. So I think in that sense, I think for instance the stochastic methods probably don't count as perturbative in that sense, and sense in which I'm not sure about some of the semi-classical pieces. But in any case, I mean, to back off to is this fully satisfactory? My starting point was I think the theory is satisfactory in about the same way as a non-gravitational quantum field theories are satisfactory. I mean, there's also theories where we have some window into their non-perturbative sectors, but where our calculational access to them is very strongly through perturbation theory. And those are also theories which are effective field theories. They need to be cut off in order to be rigorously mathematically defined, well, not even rigorously, even to be non-pathologically mathematically defined. So I want to know, I'm absolutely keen on saying let's keep exploring the theory. Let's explore its non-perturbative sectors. But the theory itself isn't perturbative, and I think the theory's limitations and infelicities overlap quite a lot with limitations and infelicities we're kind of used to in quantum field theory in general, including in the standard model.
Okay, I understand your point, but then I mean, what I'm getting at is that you sort of made a very controversial, let's say, statement that you actually said, no, we actually do have a theory of quantum gravity available. So I was asking about this satisfactory or not satisfactory in that sense, because some other people may argue that no, low energy quantum gravity is far from satisfactory.
Well, I guess one of the meta points of the talk would be that people are using quantum gravity in a lot of different ways and sometimes saying inconsistent things as a result. But I suppose, look, I want to say, we have a satisfactory theory of chromodynamics, and we have a satisfactory theory of the electroweak interaction. And of course, there are different levels of satisfactory. One might say absent a full ultraviolet complete version of those theories, absent a full understanding of the non-perturbative sectors of those theories is not satisfactory yet. So you could say, look, we don't have a satisfactory theory of particle physics. I want to say, insofar as you've got a satisfactory theory of particle physics, we've got a nearly as satisfactory understanding of quantum gravity at low energies. Again, I don't want to exaggerate that, but that's the rough shape of the claim.
Right, I agree. Thank you.
Thank you. Next question is by Ding Jia.
Hi, David. Thanks for the nice talk. I have a comment and a question. The comment is about your overall message that we have a quantum theory of gravity. I agree a lot with this message. And I think I have a lot of gratitude for you to express this, because this comes up a lot in the discussions with people in quantum foundations that grew an interest in quantum gravity. And sometimes they ask questions like how you put spacetimes in superposition, how you superpose causal structures. And some people, they treat this as open question. But I agree with your message that we have a theory of quantum gravity, and we have a clear answer to these questions. It's just, let's put space-time in superposition by doing a gravitational path integral. That's the answer. Now, I have a question, though, about effective field theory of quantum gravity. This has to do with cutoffs and momentum space. So, it's common in the literature to define the cutoff in momentum space. That's what particle physicists do. But I found it hard to understand in the context of quantum gravity, because usually I understand momentum space as coming from a flat space-time background. Now the question is, if I'm on a curved space-time background, how do I obtain a momentum space, and then how do I impose a cutoff? That's something that always confuses me.
Yeah, good. I mean, I've wondered about some of these things myself. I mean, there's sort of let me give two different answers. One is what I think you could do in theory, and one is what do people do in calculations. And the calculational answer is usually that they do it in a particular sector. So, for instance, a good example of this is doing calculations of black hole entropy, where I need to renormalize the theory. I want to work out like one loop corrections to the Bekenstein-Hawking entropy, and I have to renormalize the theory. And I'm treating the theory as fluctuations around the Schwarzschild solution, and then I'm imposing some cutoff on that framework. And you have the usual move in quantum field theory, where conceptually high momentum cutoffs are the best thing to think about because they seem the most directly physical, but calculationally they're a bit of a pain. So what you normally then do is you kind of argue that the high energy physics doesn't matter except insofar as it renormalizes terms. And then you cut off the high energy physics in some flatly unphysical way, like a dimensional regularization or some fictitious particle or something. And people tend to use that technology in calculations. What you could do conceptually, I mean, this is only my own thinking about this, but one way to think about it is what I'm doing ultimately is I'm restricting the path integral. And one way to restrict it is just to say, at least as far as integrals over G is concerned, that I'm restricting my integral to be over metrics where the curvature is never above a certain value or something.
Do people actually do this, the later point?
I've never seen anyone actually do that. It was just as a conceptual, how would I think of it? I mean, the reality is, as always in QFT, you're almost never doing a calculation in the kind of full space of the theory. You're almost always localizing around some sector and working in that space. And I was saying at various points, the theory is under somewhat less good control than non-gravitational quantum gravity. I think this is actually, you put your finger on one of the places in which it isn't under such good control. I mean, you can impose your renormalization scheme at least often in normal quantum field theory without prior to saying I'm exploring a certain subregion of solutions. It's much harder to do that in quantum gravity because normally I impose my cutoff with respect to a certain background. So trying to specify it in a way that's just complete across the theories is sort of unclear. My kind of restrict your integral to low curvature things was more trying to explore what a proof of concept of that would be rather than something you could use calculation.
Thank you, that's clear.
Thank you. Is there any other question? Well, I do have another question for you. Would it be possible that you explain again, please, why you believe that the value of the cosmological constant is an anomaly in low energy quantum gravity?
Okay, good. So just calculationally, if low energy quantum gravity is true, then the observed value of the cosmological constant is the sum of a bare parameter in the gravitational action, the bare cosmological constant, if you like, plus an expectation value of that you can calculate using QFT methods. That's not an independent posit of the bare claim that low energy quantum gravity is correct. That's just something you can calculate. So then the bare term, sorry, the quantum correction term, the bit you can calculate, picks up contributions from quantum fluctuations and also from condensates but the fluctuation terms dominate. And the energy of the fluctuations is, or the numerical value of the fluctuations in appropriate units is about 120 orders of magnitude larger than the observed value of the cosmological constant. So to make the calculation work, you now need to choose the bare value to almost exactly cancel that out. You need to choose it to cancel it out to 1 part in 10 to the power 120. So the bare cosmological constant needs to be another very large number, and it needs to be a very large number of a very precise form. It needs to have the right form to 120 decimal place and 120 significant figures. So there is a general line of thought in particle physics that's associated to issues of naturalness and hierarchy, that extreme fine-tuning of this kind is somehow pathological in theory. There's a fair amount of debate as to why that might be. I didn't try to defend it in this talk. I could give you defense, but it would be might be somewhat off topic. Roughly, I think it's to do with the fact that low energy physics ought to sort of emerge naturally from high energy physics. We shouldn't have to tune the parameters of high energy physics so that we only get the low energy physics in some incredibly small region of parameter space. I call it an anomaly because it's a problematic feature of the theory we don't understand, but it's not a flat falsification of the theory. I mean, if you calculated the cosmological constant in the theory and the calculation just flatly delivered an answer that was 120 orders of magnitude larger than the observed measure, then that just counts as a falsification. That says, okay, with some aspect of the theory may still be getting at the truth, but the theory is clearly just wrong. And we'll need to look at some modification of the theory to sort it out. This isn't that kind of problem. This is a case where a straightforward calculation plus what looked like an innocuous assumption leads to a contradiction of experiment. And so it puts pressure either on the theory or on the kind of principles we use to make that innocuous assumption. It becomes a sort of puzzle we're not sure about, but as I say, it falls short of being a falsification of the theory.
But so this tentative explanation of the origin of the cosmological constant relies on the idea that it should come from energy fluctuations of the vacuum, right?
It doesn't rely on that idea. That's just something you calculate.
But is it something that you would do the same for other fundamental constants? Like, would you also compute G or H bar?
Yeah, well, H bar you'd probably absorb into a choice of units, but G, sure. And generally, parameters in QFT work this way. So the measured parameters in a quantum field theory are, okay, it's a quick quantum field theory digression, that the measured parameters in a quantum field theory are equal to the bare parameters plus some quantum corrections to those parameters. In the old days, we thought the bare value was infinity, the quantum corrections were infinity, and they magically came down to a finite number. Since Wilson and people sort of rethought renormalization theory in the 70s, we now would think that there's a finite but high energy cutoff, and the bare parameters refer to the unknown physics at the cutoff, and the renormalized parameters kind of absorb corrections from the unknown physics into the value. But normally the quantum corrections aren't super, although they would be formally infinite if the cutoff was infinite, they're actually not super big, because normally speaking they scale logarithmically with the ratio of the cutoff to the energy scales you're at. So for instance, the correction to the charge of the electron from quantum effects is something like or to the fine structure constant is something like the square of the fine structure constant times log cutoff over the mass you're working at. And because logs go up so slowly, that's still a relatively small correction. So you could get the electron charge is quite small in natural units relative to what you'd expect from the cutoff, but you can get quite a small value just by supposing that the initial value is quite small, and there's no obvious reason it shouldn't be. In the case of the cosmological constant, and also in the case of the Higgs boson, mass as a point of interest, then the corrections scale quadratically with the cutoff, not logarithmically. So that makes the quantum corrections really extremely large, much larger than the actual measured value of it. So that then requires this extremely precise cancellation of the quantum corrections with the bare parameter that's set by high energy physics.
Okay, thanks.
I mean, there's room to get off this boat. The naturalness, these sort of naturalist arguments in quantum field theory are not uncontroversial. I think they're sensible arguments, although I think the fact they fail therefore tells us something really puzzling. But there are people who say the arguments aren't reasonable. But I suppose the cosmological constant problem requires a combination of two things. You need to buy this general particle physics principle, but then you also need to buy the arguments that says indeed the observed cosmological constant is has a big contribution from quantum fluctuations, and it's that second argument where I think if you're just sort of thinking that it's a series of speculative assumptions about future physics, then you can be doubtful of it, even if you think the particle physics naturalist argument is reasonable. But if you buy low energy quantum gravity, it's just forced on you calculationally.
Mm-hmm. I see. Thank you. Is there any question? No more? Well, then, thanks again, David, for your talk. Thanks you a lot for
the invitation.
And thank you everyone for Ding. Is it a new hand that you're raising?
Can I ask one more question?
Then sure.
Thanks, David.
Because it seems there's a lot I want to talk with David. Now there's an opportunity. So I'm curious, David, what's your thoughts on the other approaches of quantum gravity? The so-called non-perturbative approaches. My favorite is quantum Regge calculus. There are other spin foams, causal dynamical triangulations, causal sets.
Yeah.
What are your thoughts on these?
So most, I mean, much of this is something I'm not familiar with in detail. Those programs I understand tend to be looking for an ultraviolet complete theory. I mean, string theory or loop quantum gravity fairly clearly aiming at ultraviolet complete theories. And I think reproducing low energy quantum gravity is kind of a success criterion for theories of that kind, or it's a defeasible success criterion. And one sometimes thinks that what we need to get out of an ultraviolet quantum theory of gravity is that it reproduces non-gravitational quantum mechanics and it reproduces general relativity. And that was what I would have thought until like 5 or 6 years ago when I started thinking about this stuff. I think it's clear it actually needs to reproduce a lot of quantum gravitational phenomena. Our ultraviolet quantum gravity theory needs to explain white dwarfs, for instance. The way string theory pretty explicitly thinks about the goal here is it needs to reproduce low energy quantum gravity full stop. That needs to be a limiting case of string theory and effective field theory approximation to string theory. And I think a bunch of other approaches to quantum gravity to varying degrees also by that success criterion, but I'm not so sure for some programs, and it's an interesting check. Some of these programs, I mean, causal set theory is a good example, I think, are sufficiently embryonic in how much they've done in detail that it's premature to see whether or not they managed to reproduce the low energy quantum gravity theory. String theory, the case that can do it is pretty good. Loop quantum gravity, I don't know. At one point, it was thought to be a serious problem for loop quantum gravity that getting out Minkowski spacetime was difficult. But it's a long time since I knew the details of the field. So yeah, I mean, mostly I think these things are not in competition with low energy quantum gravity. Reproducing low energy quantum gravity is what they ought to be aiming to do. If they fail to reproduce it in some as yet untested regime, that would be terrific because we could actually test, it would suggest a sub-Planckian experiment we could do. If they're actually in conflict with low energy quantum gravity, i.e. if they're making sub-Planckian quantum gravity claims that are, sorry, it's lower than Planck-scale quantum gravity claims that are in conflict with low energy quantum gravity, then I think there are some urgent questions to ask how those fit with experiment. The particular Regge calculus example you give, I don't know at all, so I can't say in detail.
I see. It seems to me this question could be, this challenge could be met, say, by quantum Regge calculus. If you want to recover flat spacetime background in a classical limit, we have a path integral, so we need to impose some boundary conditions. Mm-hmm. And then to look for a classical approximation, it's just we look for the stationary points of the action. And then if we have a quantum gravitational action that reproduces Einstein-Hilbert action in a continuum limit, then there's no reason to doubt that we'll get flat spacetime solution as a stationary point.
Yeah, that seems reasonable enough.
Okay.
I mean, and that would seem to be embracing the idea that would be a success criterion. I mean, when I came into thinking about this, is I would have said up to 5 or 6 years ago that quantum gravity was, as people said, a combination of quantum mechanics and gravity. We didn't have one, and the empirical requirement for it was to reproduce quantum mechanics and separately reproduce gravity. And I now think I want to say we need to distinguish between a low energy quantum gravity theory that we basically already have and an ultraviolet quantum gravity theory. And the success test for an ultraviolet quantum gravity theory is to reproduce low energy quantum gravity.
Okay. I have more questions, but I'll let Pierre decide.
No, I mean, as for me, I have time. So if David is willing to.
Okay. Well, I'm not rushing off, so I'm happy to keep talking.
So sorry?
I'm happy to keep talking. I'm not rushing off.
Great. One more question is about the principles in QFT. Some people study in the context of a gravitational effective field theory, like causality, unitarity. Basic principles of that we really trust in particle physics for matter degrees of freedom. But there are questions to doubt them in the context of gravity.
Yeah.
Yeah,
I don't know, and at a meta level, I don't know how much that's just that I don't know those particular areas of the literature and how much it hasn't been fully thought about. I mean, here's a general observation. I gave quantum gravity in the path integral formulation. I didn't give it in the sort of alternative operator valued fields on space-time formulation. And that's not accidental. I mean, for relatively clear reasons, understanding quantum gravity in the non-perturbative sector as a theory of a background on which is defined operator valued fields is going to be a nightmare. For instance, the causality reasons you give. Normally, when we define a quantum field theory that way, then we want space-like separated operators to commute, and the notion of space-like separation isn't defined prior to having metric facts. That doesn't cause any problems inherently for the path integral, and I think as a literature point, part of the issue here is that people who've been thinking about and worrying about some of these issues of causality and the like in quantum field theory and have been for a long time, find path integrals kind of unacceptably mathematically badly behaved and have tended to want to formulate them in other contexts. But I think there are interesting questions about just what the connections there are. I mean, once you move to my guess is something like this: once you move to a particular background field regime, now of course my background field is available for me to define the space-time on which my quantum fields are stated. So I can certainly recover a kind of operators on operator valued fields understanding in those regimes, but I probably can't in full generality. And that makes you worry about whether we understand what the Hilbert space of the theory is and whether we even know how to say what unitarity is. So I think those are at least open questions in the shallow sense that I don't personally know the answer. I suspect they're open in a slightly broader sense. These are again ways in which my qualifier that we have the theory under moderately good theoretical control is applicable.
One final question about the many worlds interpretation.
Sure.
This interpretation is usually stated with respect to the Hamiltonian formalism of quantum theory. Now, for quantum gravity, you have a path integral theory. So how do you reconcile these?
Sure. So I don't think it's a huge problem doing many worlds quantum mechanics in the path integral formulation. I mean, there are some interpretive questions it raises, but roughly speaking, you want to say that what I need to get out of my theory, the way I think about many worlds in any case, what I need to get out of my theory is a sort of branching space of decoherent histories. And then I interpret that as sort of emergently probabilistic, but the underlying physics is still the whole collection. And doing decoherent history theory in the path integral formulation is fine. In fact, it's in applications of decoherent history theory, it's often actually done in the path integral formulation. So at that technical level, I think it's fine. I think there are some legitimate, deeper questions about whether some of our conceptual understanding of the average interpretation relies on the Hilbert space framework, and whether there's a good way of phrasing it in a completely self-contained path integral way. I mean, it would be nice to have that. It would be, I mean, it's generally a feature of the way path integrals are used in physics that we initially introduce path integrals as a calculational method we can use for an underlying Hamiltonian quantum theory. And then they kind of have a life of their own, and we start thinking you can formulate the theory just as satisfactorily in the path integral framework as the Hamiltonian framework. But then things like what unitarity is starts to become a little opaque. So I'm not completely sure what I should say here.
What's your thought on branching? Because usually this is stated with respect to some time, some preferred time variable. If you lose this in a gravitational path integral,
I think that's okay. I mean, I just need to have I can express my consistent histories. I mean, it's okay conceptually. Calculation is probably hideous. You know, defining observables in gravity, in the Hamiltonian sense, even in gravity, without access to some background is extremely fiddly. But in principle, nothing prevents me just writing down a sequence of, doing some gauge fixing, at least in principle, and then writing down a series of projectors according to that gauge fixing. And the actual measured time coordinate will look different in different branches, but I didn't think there's a problem of principle, and there's a hideous calculational problem. I mean, look, this is a special case of a general point. My path integral was extremely formal. I mean, I need to gauge fix. I need to only integrate once over each over each class of gauge equivalent, diffeomorphism equivalent metrics. Now, just doing that by writing at the bottom of the integral gauge fixed is conceptually okay, but if you actually want to do a detailed calculation, you need a gauge fixing condition. I mean, in QCD we do it with ghosts. You can use that technology in quantum gravity. I had to say it's over my pay grade how that works in detail, and I'm not sure I know what the sort of full conceptual situation should look like.
Great.
I mean, I think these are good questions to explore. I think this is one of the virtues of trying to put the theory in a relatively clean form is so that we can see, okay, where are the places where even once we allow for the fact it's a non-renormalizable quantum field theory, there are still things that are confusing even by the standards of those theories, and then there's room to sort of push at them more.
Can I just make a short comment, if it's okay, that if you compare the Hamiltonian formalism and the path integral formalism, the path integrals are a little bit more general in the sense that they work over manifolds of arbitrary topology. And the standard Hamiltonian approach requires, the globally hyperbolic space-time and such a thing. So in that sense, there is they're not entirely equivalent, but to a large degree they can be made. So
yeah, no, point taken. I guess there's a question about whether you'd hope that your eventual ultraviolet theory had a satisfactory Hamiltonian formulation, but it wouldn't look like the Hamiltonian formulations on fixed manifolds. That's for sure. I mean, I think this was, as a historical comment, I think this was disputed in the sort of 70s and early 80s when people were doing path integral quantum gravity, and I think the fact that Gibbons and Hawking's calculation of entropy required you to sum over different over manifolds of different topologies was regarded as contentious.
Yeah, sure.
Okay, thank you again, David, and thank you everyone.
Thanks for the opportunity. I enjoyed it.
Yeah, so have a good day, everyone, and see you next time for the next QISS seminar. Bye.
Bye.